Welcome! In this session, we'll tackle LeetCode problem number 1708, titled Largest Subarray Length K. Together, we will explore different approaches to solve this problem efficiently. Let's dive in. In this problem, you're given an integer array called nums and an integer k. The goal is to find the largest subarray of length k within nums and return it. Now, the term largest here is based on lexicographical order. This means we're comparing subarrays element by element, starting from the first index, until we find a difference. If I is greater than I at the first differing index, subarray A is considered larger. If one subarray is a prefix of the other, the longer subarray is considered larger. The input consists of the array nums and an integer k, while the output is the largest lexicographical subarray of length k as a list of integers. Let's start with some examples to understand this better. In the first example, nums is 1, 4, 5, 2, 3, and k is 3. This means we need to find the largest subarray of length 3. The possible subarrays are 1, 4, 5, 4, 5, 2, and 5, 2, 3. When we compare these lexicographically, 4, 5, 2 is larger than 1, 4, 5, because 4 is greater than 1. Then, 5, 2, 3 is larger than 4, 5, 2 because 5 is greater than 4. So, the output is 5, 2, 3. In the second example, nums is 9, 8, 7, 6, 5, and k is 2. The possible subarrays are 9, 8, 8, 7, 7, 6, and 6, 5. The largest subarray lexicographically is 9, 8, so that's the output. In the third example, nums is 1, 1, 1, 1, 1, and k is 1. All the subarrays of length 1 are 1. Since there's no variation, the largest subarray is simply 1. Now let's consider the constraints. The size of the array nums is n, and both k and n are bounded by 1 equals k equals n equals 10⁵5. This ensures that the problem is computationally feasible for large inputs. Additionally, the values in nums are non-negative integers ranging from 0 to 10 to the power of 9, meaning we are working with potentially large numbers but still within manageable bounds. Now, let's discuss a few important edge cases you might encounter. First, if all elements in nums are identical, any subarray of length k will be the largest since they are all the same. For example, if nums is 1, 1, 1, 1, 1, and k is 2, the output is 1, 1. Second, if k is equal to n, the only subarray of length k is the entire array itself. For instance, if nums is 3, 2, 1, and k is 3, the output is 3, 2, 1. Lastly, if the array is in strictly decreasing order, the first subarray of length k is the largest. For example, with nums as 5, 4, 3, 2, 1, and k is 2, the output is 5, 4. These scenarios help clarify how the solution behaves under different conditions. To solve the problem of finding the largest subarray of length k, one basic approach is the brute force method. Here, the idea is straightforward: generate all possible subarrays of length k and then select the largest one in lexicographical order. To do this, we iterate through all valid starting indices I such that the subarray nums, I plus k, is within bounds. For each of these subarrays, we compare it to the largest one we've encountered so far. By the end of this process, we will have the largest subarray. However, the downside of this approach lies in its inefficiency. Generating all subarrays and performing lexicographical comparisons involves significant computational overhead. Specifically, the time complexity is O(n)k*, which grows quickly with larger inputs. While simple to implement, this method is impractical for larger arrays or larger values of k due to its high computational cost. A more efficient alternative is the sliding window approach. Instead of examining every possible subarray, we can streamline the process using a sliding window to focus only on the necessary comparisons. The key insight here is that the lexicographical order of subarrays can often be determined by comparing their starting elements, allowing us to avoid redundant evaluations. As we iterate through the array, we consider each subarray starting at index I and of length k. We then track the index max_start of the lexicographically largest subarray seen so far. By leveraging the property of arrays where comparisons can terminate early upon finding a difference, this method improves efficiency. While still not optimal for all cases, the sliding window method is significantly faster than brute force, with a time complexity of O(n*k). However, for very large k values, this approach can still be suboptimal due to the linear cost of subarray comparisons. To further optimize, we used the greedy approach, which eliminates unnecessary comparisons by focusing solely on maintaining the largest starting index as we iterate. The critical observation here is that we don't need to compare entire subarrays. Instead, we can stop the comparison as soon as we identify a difference. For each valid starting index I, we compare the subarray nums, I plus k, with the subarray starting at max_start, updating max_start whenever a larger subarray is found. This approach leverages early termination during comparisons, significantly reducing the time required. In terms of complexity, this method operates in O(n) on average, as comparisons between subarrays are often resolved quickly. Even in the worst case, it remains highly efficient compared to the previous methods. The greedy approach is particularly well suited for larger arrays and subarray lengths, making it a strong candidate for solving this problem efficiently. The strategy we chose to implement is the greedy approach, as it strikes the best balance between simplicity and performance. Unlike the brute force or sliding window methods, it avoids unnecessary subarray comparisons, achieving near O(n) performance in practice. The breakthrough realization with this method is that lexicographical comparisons can terminate as soon as a difference is found, drastically reducing redundant computations. This makes the approach both elegant and powerful. We opted against the brute force method due to its prohibitive computational cost, and while the sliding window approach is an improvement, it still struggles with inefficiencies when k is large. The greedy method, on the other hand, is efficient even in the worst-case scenario and requires minimal adjustments to handle edge cases. These advantages make it the most practical and scalable solution for this problem. To solve this problem, we need to identify the subarray of length k that is lexicographically the largest in a given array of integers. Lexicographical order here means comparing subarrays element by element as you would compare words in a dictionary. A simple approach to solve this is the brute force method. In this approach, we generate all possible subarrays of length k and compare them to find the largest one. The process involves initializing a variable, max_subarray, to track the largest subarray found so far. Then, we loop through all possible starting indices for subarrays of length k, extract the subarray for each starting index, and compare it to max_subarray. If the current subarray is larger, we update max_subarray. Finally, after processing all subarrays, we return the largest one. While straightforward, this method can be computationally expensive due to the large number of comparisons required, especially for larger arrays. The brute force method, though simple, has a significant computational cost. Generating all subarrays of length k requires iterating through the array nk plus 1 times, where n is the length of the array. For each starting index, comparing subarrays takes k time. As a result, the overall time complexity is nk plus 1 *k, which can become inefficient for larger inputs. Let's consider an example to better understand this approach. Suppose the input array is 3, 5, 2, 6, and k is 2. The possible subarrays of length 2 are 3, 5, 5, 2, and 2, 6. Comparing them lexicographically, 3, 5 is smaller than 5, 2, and 5, 2 is smaller than 2, 6. Therefore, the largest subarray is 5, 2, which becomes our output. This example illustrates the concept but also highlights the inefficiency of generating and comparing all subarrays. To address the inefficiency of the brute force method, we can use an optimized approach called the sliding window. The key insight here is that we don't need to generate all subarrays explicitly. Instead, we can slide a window of size k across the array and keep track of the lexicographically largest subarray encountered so far. This approach eliminates redundant comparisons and focuses only on contiguous subarrays. We start by initializing an empty list, result, to store the largest subarray. For each possible starting index of the sliding window, we extract the subarray of length k and compare it to the current result. If the new subarray is larger, we update result. By the end of the iteration, result contains the largest subarray. The time complexity of this method is O(n), as we process each element at most once, and the space complexity is O, K, to store the result. This optimized approach is faster and more suitable for larger inputs. In implementing this solution, we rely on basic data structures like arrays to store the input and extract subarrays, and a list to store the result. There are also a few important edge cases to consider. If the length of the input array is smaller than k, we simply return an empty array since no subarray of the required length exists. If all elements in the array are equal, any subarray of length k will be valid as they are all identical. Negative numbers are handled seamlessly, as lexicographical order applies regardless of whether values are positive or negative. Let's look at a visual example to bring this all together. For the input array 4, 9, 1, 3, 7, and k equal to 3, we process sliding windows. The first window, 4, 9, 1, becomes our initial largest subarray. The next window, 9, 1, 3, is larger and replaces the previous result. The final window, 1, 3, 7, is smaller, so the result remains 9, 1, 3. This illustrates how the sliding window approach efficiently identifies the largest subarray. This implementation solves the LeetCode problem number 1708, largest subarray length k. The task is to find the lexicographically largest subarray of length k in the given list nums. We start by defining the class solution and implementing the largest subarray method. The method takes two arguments, nums, the input list of integers, and k, the desired subarray length. First, we initialize max_start to 0. This variable keeps track of the starting index of the largest lexicographical subarray found so far. We assume the subarray starting at index 0 is the largest initially. Next, we iterate over possible starting indices for subarrays of length k. The valid range for these indices is from 1 to n, nums, k, inclusive. At each step, we compare the current subarray nums, I plus k, with the subarray starting at max_start. Python's list slicing and comparison operators make this comparison straightforward, as lists are compared lexicographically by default. If the current subarray is lexicographically larger than the one at max_start, we update max_start to the current index I. Finally, after the loop completes, max_start points to the starting index of the largest subarray. We return the subarray nums, max_start plus k, as the result. This approach ensures we only loop through the list once, making the time complexity O, n, where n is the length of the input list. The space complexity is O, 1, as we only use a few variables and no additional data structures. Here, we start implementing the solution for finding the largest subarray of length k. First, we import the required Java utilities and define our solution class. Inside this class, the method largest subarray takes an integer array nums and an integer k as input. The goal is to determine the starting index of the lexicographically largest subarray of length k. We initialize a variable max_start to 0, which will track the starting index of the largest subarray found so far. Then, we use a for loop to iterate through all valid starting indices of subarrays of length k. For each starting index I, we compare the subarray starting at I with the one starting at max_start using the helper method isGreater. If the subarray starting at I is lexicographically larger, we update max_start to I. Once the loop completes, we construct the result array by copying the subarray of length k starting at max_start into a new array, which is then returned as the result. The helper method isGreater is defined to compare two subarrays of length k. It takes the array nums, two starting indices start1 and start2, and the length k as input. The method iterates through each element of the two subarrays, starting from their respective indices. For each pair of elements, if the element in the subarray starting at start1 is greater, the method immediately returns true, indicating that this subarray is lexicographically larger. Conversely, if the element in the subarray starting at start2 is greater, the method returns false. If the elements are equal, the loop continues to the next pair. If all elements are equal after comparing the first k elements, the method returns false, as neither subarray is greater. This helper function ensures an efficient comparison of subarrays to assist the main logic in identifying the largest subarray. To solve this problem, we start with an example where the input array is nums equals 1, 4, 3, 2, 5, and the subarray length k equals 2. First, we initialize max_start to 0, which will track the starting index of the largest subarray. The goal is to iterate through all valid starting indices and compare subarrays of length k to find the lexicographically largest one. The loop begins at index I equals 1 and ends at I equals 3, since the last possible subarray starts at len nums k equals 3. In the first iteration, where I equals 1, the current subarray is 4, 3. Comparing this with the subarray starting at max_start, which is 1, 4, we see that 4, 3 is larger, so we update max_start to 1. In the next iteration, where I equals 2, the current subarray is 3, 2. This is smaller than 4, 3, so max_start remains unchanged at 1. For the final iteration, where I equals 3, the current subarray is 2, 5. Comparing this with 4, 3, we see that 2, 5 is also lexicographically smaller. Thus, max_start stays at 1. After completing the iterations, the largest subarray is the one starting at index 1 and spanning 2 elements, which gives us 4, 3. Now, let's examine a second example with a different input, nums equals 9, 8, 7, 6, 5, and k equals 3. Here, we initialize max_start to 0 again, and the loop will run from I equals 1 to I equals 2 since the last valid subarray starts at len nums k equals 2. In the first iteration, where I equals 1, the current subarray is 8, 7, 6. Comparing this with the initial subarray 9, 8, 7, we find that 8, 7, 6 is smaller, so max_start remains 0. Next, in the second iteration where I equals 2, the current subarray is 7, 6, 5. This is also smaller than the subarray 9, 8, 7, starting at max_start, so max_start does not change. After completing the iterations, the largest subarray is the one starting at index 0 and spanning 3 elements, resulting in 9, 8, 7. Now, let's consider another example where the input array is nums equals 4, 4, 4, 4, and k equals 2. Once again, we initialize max_start to 0. The loop will run from I equals 1 to I equals 2. In the first iteration, where I equals 1, the current subarray is 4, 4. Comparing this with the subarray starting at max_start, which is also 4, 4, we find that they are equal. Therefore, max_start remains 0. In the second iteration, where I equals 2, the current subarray is again 4, 4. Comparing this with 4, 4 from the existing max_start, we see that they are still equal. As a result, max_start remains unchanged at 0. After completing the iterations, the largest subarray is 4, 4, starting at index 0. This example demonstrates how the algorithm handles cases where all elements in the array are the same. The comparison logic ensures that the first occurrence of the largest subarray is selected when there are ties. To summarize, this algorithm systematically identifies the lexicographically largest subarray of length k by iterating through all valid starting indices and comparing the subarrays. The key steps involve initializing max_start and updating it whenever a larger subarray is found. The time complexity of this approach is O and *k due to the slicing comparisons, and the space complexity is O, k for storing slices during comparisons. While this method is efficient for small to medium-sized arrays, optimizations might be needed for very large inputs. This step-by-step process ensures correctness and clarity in determining the largest subarray. The time complexity of the solution primarily depends on the for loop, which iterates through all possible starting indices of subarrays of length k. Specifically, the loop runs from I equals 1 to len nums k, meaning it executes in k iterations, where n is the length of the input array nums. Within this loop, the slicing operation nums I plus k extracts a subarray of length k, taking O, k, time, and the comparison of two subarrays of length k also requires O, k, time. Since these two operations dominate each iteration, the time complexity for one iteration is O, k. When combined over all n k iterations, the total time complexity becomes k *O, k, which simplifies to O, n k *k. In the worst-case scenario, where k is much smaller than n, this is commonly expressed as O, n *k. The space complexity of the solution is relatively straightforward. Since the input array nums is not modified, no additional space is required for storage beyond the input itself. The slicing operation nums I plus k creates temporary subarrays of length k during each iteration. However, these subarrays are not retained in memory after each comparison, they are discarded immediately. Therefore, the space used for slicing at any given moment is OK. Apart from this, the solution uses only a few variables like max_start, which require constant space or O1. When we combine these factors, the overall space complexity of the algorithm is determined to be OK, due to the temporary subarrays created during slicing. To compare this approach with a brute force solution, consider the naive method that would generate all possible subarrays of length k and then compare them to find the largest one. This brute force method involves creating n k plus 1 subarrays, where each subarray requires OK time to generate and compare. As a result, the total time complexity is n*k, which is similar to the optimized approach we analyzed. However, the brute force solution has a significant drawback in terms of space complexity. Since it would need to store all nk plus 1 subarrays, its space complexity would be n*k, which is far worse than the optimized solution's OK. When analyzing the best, average, and worst cases for this algorithm, the time complexity consistently remains n*k, because all iterations are necessary to ensure correctness. Overall, this optimized approach is both time-efficient and space-efficient, avoiding the overhead of storing unnecessary subarrays while maintaining a manageable computational cost. When solving this problem, there are a few common mistakes to be aware of. First, many candidates overlook edge cases. For example, what happens if the input array is empty, if the value of k is larger than the array length, or if k is 0? Ignoring these scenarios can lead to runtime errors or incorrect outputs. To address this, you should always validate the input and handle these cases explicitly by returning an appropriate result, such as an empty subarray or an error message. Another common issue is performing numerical comparisons instead of lexicographical comparisons when evaluating subarrays. Remember, lexicographical order treats the elements as strings, so this distinction is critical when the array contains multi-digit numbers. Always convert numbers to strings when comparing if the problem specifies lexicographical order. Finally, many candidates rely on brute force methods and fail to optimize their approach. This can lead to high time complexities, like n² or n*k, which are inefficient. Instead, you should leverage the sliding window technique, which reduces the time complexity to n, and is well suited for problems involving fixed-length subarrays. Another frequent challenge is misunderstanding problem constraints. For instance, assuming all elements are positive or that k is always valid can result in solutions that fail under certain test cases. To avoid this, carefully read the problem statement and ensure your solution respects all constraints. Off-by-one errors are another pitfall, especially when calculating subarray boundaries. These errors can cause you to exceed array limits or select the wrong range, so it's important to double-check your boundary conditions and use clear, descriptive variable names to help avoid confusion. In interviews, it's crucial to fully understand the problem before diving into the solution. Take the time to clarify edge cases and constraints with your interviewer. This not only helps you avoid mistakes but also demonstrates a structured approach to problem solving. Additionally, optimization is often a key focus during interviews. Be ready to explain why your solution is efficient and how it compares to simpler or brute force alternatives. Finally, a strong understanding of data structures, like sliding windows or priority queues, is essential. These tools often form the backbone of optimized solutions, so knowing their time complexities and how they work is invaluable. Don't forget to think out loud during interviews. This shows your reasoning process, especially when iterating from a basic solution to a more efficient one. This problem has connections to several related problems on LeetCode. For example, LeetCode 239, sliding window maximum, is another sliding window problem where the goal is to find the maximum value in every window of size k. Similarly, LeetCode 402, remove k digits, involves selecting subsequences based on lexicographical order, which is directly relevant here. LeetCode 321, create maximum number, also requires forming the largest number by selecting subsequences, and LeetCode 1423, maximum points you can obtain from cards, applies a sliding window technique to optimize the sum of elements. Exploring these problems can deepen your understanding of related techniques. Now, when it comes to alternative approaches, the brute force method is a straightforward option. This involves generating all possible subarrays of length k and comparing them lexicographically. While this approach is simple to implement, it has a time complexity of n*k, making it inefficient for large inputs. It's a good starting point for understanding the problem, but optimization is necessary for more complex scenarios. A more efficient approach is the sliding window technique. Here, you maintain a window of size k as you iterate through the array, updating the lexicographically largest subarray whenever a better candidate is found. This reduces the time complexity to n, but careful implementation is required to manage the window updates correctly. Another advanced method involves using a deque or monotonic queue to keep track of the indices of the largest candidates within the current window. This approach also achieves n time complexity but can be more complex to implement. Finally, there's the option of using binary search on indices. This involves leveraging binary search to find the lexicographically largest subarray, yielding a time complexity of n*log n. While this method can be useful in scenarios with additional sorting constraints, it tends to be less intuitive than the sliding window technique. Each of these approaches has its trade-offs, so selecting the right one depends on the specific problem constraints and requirements. Great job! In this session, you learned how to approach the largest subarray length k problem. We reviewed the brute force method and discussed optimization techniques. Keep practicing, and don't hesitate to revisit this concept whenever needed. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!